safety critical talks by talking about security in software.
Yes,
So thank
exactly.
you, Morgan.
Yeah. So good morning. We're going to perform a bit of a Rust inspection to get us awake. So I'm a bit different to most of you here. I'm a security consultant. I don't write much Rust. I do read a lot of Rust. So please format your code nicely. It makes my life easier. I basically fell into doing a lot of Rust code audits. It seems to be my niche, which is why I'm at this conference and not at some other conference right now. And I have to point out that I am a reformed DevOps. I have committed many sins against YAML, and for those I am now trying to atone. Right, so what is hopefully going to be interesting for you as mostly a developer audience is a bit of an introduction to security and application security. So application security is the domain of security that looks at your application, the software, how it is deployed, what it is constructed of, and what methodology you use to build that software. This is different to the general topic of cybersecurity, which is, have I configured my domain controller correctly? This is not what we're interested in here. We're interested in software. So that's what AppSec is. And to understand AppSec, we first have to talk about security agencies. So we have to talk about the CIA. We have to talk about these goals that we have when we think about a threat model. Is our application secure? Does it protect confidentiality? Does it protect integrity? And does it protect availability? And just to give you some examples of what I mean by each of these words, let's talk about confidentiality and what a confidentiality bug would be. So an SQL injection where I can, for example, dump the entire users table from your database, then the confidentiality of your users has been compromised. This is a confidentiality bug. Another bug that we will look at later is a path traversal bug. So typically, you might have a part of your program which serves documents, serves files, and it should only serve files from a particular directory. But paths on file systems are complicated, and you can have things like .. in them, which go up a directory. And if you don't account for that, then you can have a path traversal bug, and you can download a file from outside of a place where the files you should be able to download are from, which is also a confidentiality issue. And then there are more subtle confidentiality bugs. These would be side channels. So like the most obvious side channel I can think of to describe would be in a web application, you have a password reset form, and if you put in a email address where the user is in the database, when it takes you to the next step, if you put in an email and the user is not in the database, it doesn't take you to the next step. You've leaked one bit of information, you've leaked the confidential information that this user uses your service. This is a relatively obvious side channel, but side channels become more of an interesting topic when you talk about cryptography and constant time operations. A lot of you work on embedded, so you could also have power side channels. And there's even like crazy people who recover cryptographic information by having microphones at the other side of the data center and listening to your capacitors scream. So that's confidentiality. Integrity. We like it when our programs do what we expect our programs to do, and they do it consistently and according to our instructions and nobody else's instructions. So a traditional traditional security topic would be code injection. In Rust, code injection is quite hard. On modern platforms, code injection is much harder. The combination of Rust and modern platforms makes traditional, like, I'm going to run some shell code here, very hard, but you can still have other forms of code injection. If you've got a WASM runtime or anywhere, like even SQL, of course, anywhere where you can run something in a Turing machine, which is supposed to be in a sandbox. If you can escape that sandbox, then you have code injection, which can damage the integrity of your application. Another common thing we have, weak checksums. If you're using MD5, you can collide an MD5 hash quite conveniently. So you have your legitimate data, then you have an MD5 hash of it, and I come along with my illegitimate data and some GPU time to burn, and make my illegitimate data with some padding collide with your legitimate data, and then we've broken your integrity there. And then there are logic bugs, which many people call features, and these are paths for your application which we either designed poorly without thinking about how this feature could be used maliciously, or were left unspecified, undefined behavior, if you like, and then a weakness has evolved out of this. This is usually just a we didn't think about that kind of problem. And then there's availability, which is the most common type of bug, I would say. So panics. There are many, many ways to panic in Rust. Panicking is usually safe. Well, it's safe in a Rust sense. In most applications, it's also kind of fine. But as you'll see later, there are applications where panicking is less fine. Yeah, pretty simple. Your program ends, it is unavailable. Then there is resource consumption. Resource consumption is, for example, submitting a really complicated regex which uses a lot of RAM or a lot of CPU or a lot of network, something which inhibits your application from actually serving real user requests. Yeah, you could have this with a peripheral or something. And then there are concurrency bugs, deadlocks, any way your application can be brought into a state where it no longer functions. And in your worlds, probably the watchdog will come along and reset you, but this is temporarily unavailable. Okay, so what do we got next? So we've got the secure software development lifecycle. This is an incredibly simplified secure software development lifecycle. We like acronyms. So we start with planning. Planning is where we hopefully decide about our threat model. What matters? What is security in our application? What does our application do? What is the impact of our application misbehaving? This is also where you decide, am I going to bring in every dependency in the world? Do I need the left pad crate, or do I not need the left pad crate? These are the decisions you hopefully make about your attitude towards dependencies and what you're building and how you're building it, and also deciding on ideas like, is my application actually multiple processes? Do these processes have different levels of exposure? Can I build my application in using the principles of least privilege? These kinds of things are what you think about then. And then there's the implementation phase, which I think most of you in the room probably do, which is writing code. And when we write code, we use things like Clippy, and Clippy tells us off when we do bad things. And the compiler tells us off when we do bad things, and we like it when automated systems tell us that we are writing bad code, because this improves the security of the code we're writing. And then there's testing, and of course you all have excellent functional testing and unit tests, and it's all test-driven development and fantastic. But in a security context, I like fuzzing. Fuzzing is fantastic. If you're not fuzzing, you should start. More on that later. And then somebody like me comes along and does a pen test or an audit or both of your application. So a pen test being we actually run your application where it is supposed to run and click about it and try to find mostly these logic bugs, these paths for your application which were unintended. And an audit being more of either you give me all of your source code and I read it, or or I ask your developers difficult questions about your source code until we find something out. And that's usually quite fun, and that's why I like doing it. And then there's this phase which I could leave off because most people forget it. It's called maintenance. And this is where you make sure that your application is following the latest standards. For example, if you're hashing passwords, using the latest password hashing algorithm with the correct strength parameter. And also make sure that the dependencies you're using, if you're using any dependencies, do not have open security vulnerabilities in them. And there's an important side note here, is that just because you're using the latest version of your dependency does not mean it is not vulnerable. It just means that either no one has found a bug in it yet, or someone has found a bug in it, but it has not been patched, and maybe it is not being maintained anymore. So you also probably need a bit of thinking about, yeah, if this dependency hasn't been updated in 2 years, why has it not been updated in 2 years? and making sure you are on top of this in your maintenance phase. So that's AppSec 101. Now I'm going to use some real code examples from open source projects with real bugs that I found, which have all been long since fixed, and the developers were very, very helpful in fixing them. Just point that out. So there's going to be lots of code, but you're not expected to read all of it, don't worry. Right, so first bug. It's a directory traversal. So this is the Tauri development server, so Tauri, cross-platform application development framework, so you can develop applications for Linux, Windows, Mac OS, iOS, Android. So in this instance, you're developing an application for iOS. You've got your MacBook, and you're running this code, because this code serves your front end to be rendered on the phone while you test it, because that's convenient for development. But as you can see, we have this URI, which is a path, and we pass it directly to fsread. Okay, obvious path traversal. So what do you do? Well, you do this. You do a path traversal, and you download etc pathwd from somebody's MacBook. So the model here is you are developing your app in your cafe on your cafe Wi-Fi, and then anybody in this cafe can now download random files from your MacBook. Not so great. So easy fix. Introduce a fsread scoped function. And what does this fsread scoped function do? It canonicalizes the path. They use this Dunce canonicalize library, which basically just makes paths pretty on Windows and then palms it off to stud fs canonicalize. And canonicalization is returns canonical absolute form of a path with all intermediate components normalized and symbolic links resolved, which basically means I ask the operating system, what path will you actually give me back if I was to open this file? And once you've got this completely resolved path, then you check this completely resolved path against your path prefix, this servdir, and this, in effect, fixes the vulnerability. You technically don't need to resolve the symbolic links, but the operating system API does that, so it's the most convenient way to fix this. So whenever Tauri vulnerability, so in Tauri 2.0, they have this facility for providing scoped access per window. So you can say that one window can open the entire home directory, let's say our bookkeeping, book entry window, because we want to be able to upload receipts, we want to be able to upload invoices, but we're not going to do anything to these files in that window. So it's perfectly safe. We're just uploading arbitrary files. And then we think, because we care about security in our threat model, we've said if we open a PDF, we're not going to open the PDF in our book entry window. We're going to have a special window to do that, because PDFs are nasty and they run JavaScript and stuff, so there could be malicious stuff happening there. We're going to sandbox that. We're going to have a separate window. And that window can only open files from a temporary directory. And Tauri lets us do that. So that's great. We've built a threat model on top of this sandboxing which Tauri provides. But oops. So we have this window 1, and it's allowed to open this file. But it seems like we have the contents of this file showing up in window 2. What's going on here? So in window 1, perfectly legitimate window, we trust the code running in here. It's some JavaScript running in the web frame. And then we have some malicious code running in window 2. What is this malicious code doing? It's abusing an internal state of the Tauri application in that there's this shared resource table, and the resource IDs in this resource table are predictable. They're sequentially allocated. We can see this clearly in the code. It's just a U32, and every time we allocate a resource, we allocate a new resource ID. Very, very simple. So that is an easy way to escape the sandbox. You just iterate through all of the resource IDs. In this example, we were just reading the file. You could also write to the file. And the same thing also applied to HTTP requests as well. You could steal other Windows HTTP requests using this technique. So it was a pretty easy fix for them. They simply randomized those numbers. So now instead of just iterating through resource IDs one at a time and being fairly certain that you will find a lot in the early stage of that range. Now you have to search the entire 2 to the 32 space, so it's significantly obfuscated. You will not find one very easily. Okay, next bug, not Tavi. I've picked on them enough. So this is Rosenpass, and Rosenpass is a extension to the popular WireGuard protocol, which adds a quantum-resistant key exchange mechanism on top of WireGuard, because you'll be aware that WireGuard uses traditional asymmetric encryption, and traditional asymmetric encryption is not safe in a world where we have large quantum computers anymore. At least we haven't proven that. So we need to add the new quantum-resistant key exchange mechanisms to it. So what Rosenpass does is it adds a couple of extra messages to a WireGuard protocol, and then has to handle these messages for a WireGuard protocol. And the bug is not instantly apparent here in this code snippet, but this is the handler. The message comes in, we try to pass the envelope, and when we pass the envelope, we also pass this init hello message, and it's just a message handler. But what happens with this message handler? This is actually a case where panicking is bad, because if we panic here, then we are unable to perform our key exchange. And if we're unable to perform our key exchange, our communication has been weakened. Because the connection won't actually fall down. It doesn't break the WireGuard connection. So you will continue communicating, but you will not have the additional protection which you're running Rosenpass for. So it defeats the entire application. So as you can see, it's an out-of-range error. Why is it an out-of-range error? Well, we're not passing into structs here. We're trying to do something clever. We're trying to do this in a zero-copy way because we like to be fast and efficient and rusty. And also we're doing cryptography, and we want to allocate inside libsodium's allocator because we don't want our page of memory to be swapped out, because if our page of memory is swapped out, then we potentially write cryptographic information out in plain text to disk, which would also be bad. So we're using this data lens macro, which makes it look like we're using structs, but isn't really. So this data lens macro, where the bug's actually happening, just indexes into a slice, basically, to get those fields out. So we're not performing any length checking here, which is also good, because we don't want to length check every time we pull a field out, because that would also hurt performance. So, yeah, as you can see, when we construct for type, we don't do any length checking. Simple. That's the vulnerability, basically. So to fix it, all they did was add this truncating method, which does actually check for length of type. So you check it once, and now it's safe. It's a very easy fix. But you'll notice a theme with all of the vulnerabilities I've shown you so far. None of them involved unsafe code. You can write many bugs which actually have real-world security implications without any unsafe. Yeah. Wow, I'm going much quicker than I expected to. So now we're on to the section where I tell you to do stuff. Right, so tools. If you are not already using Clippy, use Clippy. Install it now, or maybe in the coffee break. Cargo audit is extremely useful. If you're not using cargo audit or renovate or dependabot, what are you doing? Cargo audit will give you what I would say is a high quality signal of if cargo audit says something is vulnerable, it is vulnerable, and then you need to act. So if you're not quite comfortable with getting every minor software update, then just use cargo audit. If you are comfortable with getting every minor software audit, use a dependabot or a renovate or something like this. This is what I would say is when I come into a project and you're not doing this already, we do this before I start. So typical easy wins. Fuzzing. Fuzzing is very easy in Rust. There is cargo fuzz. This will set you up with a libfuzzer harness template very quickly. If you're not doing async, it is pretty easy to get something running. If you are doing async and depending on stuff like Tokyo, then you will have a harder time doing this reproducibly and doing this in a doing this quickly, but there's an option for that I'll get on to later. But fuzzing will pretty much instantly, it will take you 20 minutes to write your first harness, and then you let it run for an hour or so, and it will find some panics, I almost guarantee it, if you've never fuzzed your code before. Yeah, just do it. Simple. You've got a coffee break coming up, so do that. Maybe there's no unsafe bugs that I've shown you, but if you're doing any unsafe, run Miri. If Miri tells you something, believe it, and then try to find somebody who can interpret the Miri output for you, and start the discussion with Miri. It's good. And then investments to consider. These are all things which are going to take you a bit more time. I'm sure you all just have prop test already because you're safety critical developers. For your typical concurrency bugs, obviously Loom is the way to do that. It will take you some time to step everything out and make it work, but do it. Tools like OV, which is really nice for doing symbolic execution. There are commercial options for this, which are nicer, but OV is open source, so you can use that for free. You're not going to symbolically execute your entire application. Maybe you do. But definitely the core code paths, you can check those, get a bit of extra assurance. And then your escape hatch, if you are doing anything very complicated. And a lot of you are doing things with embedded, so maybe you need to do this anyway. libafl. libafl is a library in Rust for writing fuzzers. So you can write fuzzers using things like QEMU, GDB, inspecting the dwarf yourself. You can do everything you've ever wanted to do, the cutting edge of fuzzing in libafl. It is not easy, not simple, but it does let you do what you want to do, and it's in Rust, so you're familiar with it. It's familiar tooling to test your software, even though you're probably going to be compiling your software and then building it and then putting it in a lightweight emulator, and it gets very complicated very quickly. It's not an easy investment, but if you need to do it, then you can do it. And that is the quickest I've ever done this talk. Fantastic. So I guess I have time for questions.
Time for questions. Thank you, Joe. So who has questions? Who found other bugs that Morgan didn't point out in his code? Who else has experience in bug hunting? No? Yeah.
Thank you for the interesting talk. I have a very, stupid question, I guess. You were referring to the problem with the incremental resource IDs.
Yes.
And suggested to use random numbers.
Yes.
I totally understand that this reduces the probability of getting an attack.
Yes.
But would you then consider this to be actually a proper mitigation of the problem?
It was so to give some context of that. I was reviewing that code just pre the 2.0 release, so it was basically in the release window. You would have to do quite a lot of changes to properly mitigate that problem. The ultimate mitigation to that problem, I would say, would be, obviously having a separate resource table per window or something like this. Or, but I think it makes it sufficiently hard to exploit, but it's not practical anymore. Because in the context of Tavi, the threat model is that an attacker runs arbitrary JavaScript in an untrusted window. You're probably not going to enumerate the whole 2 to the 32.
And that assessment, is that based on your gut feeling or experience? Or if you are really assessing this code and at the end say, that's safe.
It's going to take a sufficient amount of CPU to do that, but it's going to cause problems elsewhere. The application is going to become unresponsive if you try to search that space in JavaScript in the window. Yeah. So it was safe enough for us to say that was a reasonable mitigation. It's also the sandbox in Tavi is a best effort. It's a best effort thing. It's there to Yeah, it's there to make general purpose applications more secure. It's there to be basically just better than Electron, you know. Yeah, it's definitely better than Electron. Like, so there is, it's not like an operating system like sandbox boundary. This is, yeah. So for the purpose and for the threat model of you're not going to be running. You don't want that window to be compromised. Like you're not like explicitly trying to run bad code there. You're just running stuff you don't quite trust. So it was sufficient for the purpose.
Any other? We've got one over here.
Hey, thank you for the great talk. I absolutely agree with everything that you said, and I think more people should use these tools by default. So I just had a question, whether where did you find your first clients who order your audit? There are not so many Rust audits going on, and you somehow definitely audit the code.
Yes.
Or is it only for open source that you do your work? Or
I mean, I do work on closed source stuff too. I picked examples from open source projects because it's open talk. Yeah, these projects were actually NLNet projects. So they were funded through NLNet, and then as part of that funding, they got some funding for an audit. So I ended up doing the audit. Tavi was a really long engagement. We spent like 2 guys, 3 months doing that for the 2.0 release.
Any other questions from the audience? Here. John.
Hey, I was wondering if you had any suggestions on, this talk was primarily about AppSec, but the minute you get outside of the app, there are some, general good practices. Do you have any suggestions on tools for, the minute you kind of cross the threshold into, say, like appsec instead, like proper jailing, permissions, all that sort of stuff?
I mean, use whatever your operating system provides for you. I mean, another thing I didn't touch on at all is like, developer workstation, like operational security, like just don't YOLO install Visual Studio Code plugins, please. Like, anything which is running on your workstation can potentially be tampering with the code that you're producing. So, yeah, my suggestions would be, look at the tool you're importing before you import it. And it's the same with libraries, right? It probably costs you less to spend like 10 minutes having a brief look, a bit of a grep through a crate you're about to import versus importing this crate and then finding out that it has a Bitcoin miner in it like 2 years later,
Other questions? Up here.
You rightfully pointed out that most of these vulnerabilities happened in safe code. So there was no unsafe code in those examples, right? Like really a lot of the safety benefits that Rust gives you don't address this because the errors happen in the program logic.
Yes.
Is there actually anything about the Rust programming language that you feel makes catching these programming language bugs easier than it is compared to legacy languages, or is it?
Yeah, like if you look at the Rosenpass bug, Rust has like saved our asses from a much more serious bug where we would have like read out of bounds memory. Right. Like so, yeah. And what I find in Rust is that it's a cultural thing, not a language thing, right? There's much more emphasis on correctness. So you find most of the libraries are trying to do the correct thing, and if you find that they're not doing the correct thing, they're very, very happy to fix that. I don't know whether that will last in the long term, but if it does, that's great.
Yeah, so like in particular, I mean, it's clear that Rust gives you a more solid foundation here, since like you can make more expectations about the behavior of the code, in particular if it's in the safe section. Like if it now comes like a lot of the analysis for these kinds of problems, then like ideally you would want a tool that helps you with that also to validate that also your program behavior is correct. Do you feel that like Rust is already in a good place there with like supporting those tools, or do you feel that there is like maybe some areas for improvement where we could add things to make it easier to analyze?
Yeah, I mean, I find myself, scratching my head a lot of the time trying to test like protected private structs and stuff because, I just want to create a condition. I don't necessarily want to go through the whole application to do that. But it's not bad. I've not found a language where it works better, if I'm honest. Like most of the C++ and C tooling is all about, undefined behavior and memory safety. So a lot of the tooling which exists for C++ you don't really need for Rust. So it's a bit, that's how I generally see it.
We've got one more.
So my question is sort of a follow-up on his question, taken from a different angle. Like by looking at the bugs you showed, it seems to me that a recurrent pattern is something like accessing resources through operating system provided ways, where the operating system provided way is just too general.
Yep.
And I was wondering if an approach to mitigate this would be to sort of hint application writer not to rely on STD bare, but provide something like a secure sandboxed library to access resources. Now, there should be design involved in that. It should probably look like what WebAssembly does, like portals or things. And so an application that is striving to be secure should just decide to ban direct STD access and say, this is the actual interface to the world. Such a project, I fear it doesn't exist. So instead of asking for tooling, I would not probably do this myself, but I would suggest the community, should somebody do such a library, please, so that users don't use STD directly. Does this sound?
This sounds like totally reasonable, like how you try to keep your sort of unsafe in one place or your FFI in one place. You could say, well, talking to my operating system should be in one place. Like if you want to design your application like that, so I have like one place to look for, this is where the path traversals, this is where, all of those things are going to exist. Yeah, you could totally have a middleware that does that. I don't know whether the problems are generic enough that you would have a library that everybody just uses, but certainly you could design an application where you put all of the like plain FS, plain STD interactions in one place. But a lot of STD is like, standard result, this kind of stuff. So obviously you're going to use that.
Okay. Thank you so much, Morgan. Oh, we've got one more question. We're giving you one more. Sorry, this is a very intense question round. Here we go.
Yeah, it's a follow-up of the follow-up. So therefore, let's say, usually when you code software, you have, let's say, also a principle that you should always write code so that it's also be testable.
Yes.
Now you scratch your head because you couldn't, let's say, get a state in there for your internal struct, let's say, to do some kind of fuzzing. So therefore, you could also extend this to make also write the code so that it's also fuzzable somehow.
Yeah.
And do you have some suggestions about, let's say, design patterns or some hints, blog posts or something like this, how to, when you do not want to make this a public API, the user should never use this, you can use doc hidden and so on, but still you want to be, let's say, it should be fuzzable, so therefore, what is your suggestion here?
Yeah, like what I usually end up doing is like actually just like monkey patching it and then having a diff. So that usually works. Obviously you could use some unsafe if you like, but when you start doing it with unsafe, then you're not allowed to use the awesome trait arbitrary. So if you basically go look at the arbitrary trait, which lets you derive arbitrary versions of your structs, this is the one thing I like to implement because it speeds up developing a fuzzer a lot, and there's a derive macro for it. So I mean, if you want to like patch your software, so if you have the fuzzing compiler flag on, then it derives arbitrary on all of your structs. That would make it very easy.
Okay. Thank you, Morgan, for bringing bug hunting and monkey patching to the stage.